Welcome to the South Dakota Mines Department of Mechanical Engineering Research Seminar for fall 2020. I'm Michael Landy, and I'm excited to introduce our speaker this week, Dr. Wendy Ju from Cornell Tech. She's an associate professor of information science at the Jacobs Cornell Technion Institute at Cornell Tech. So her research focuses on interaction with autonomous systems such as automobiles and robots, and we were together getting PhDs in the Center for Design Research at Stanford University. So I'm excited to welcome Wendy and her talk today. So I'll hand it over to you, Wendy. Thank you.
Thanks. I just want to say I'm actually happy. I know there's only so many people here, but I've given this talk before. I only need to listen to myself talk so much. If anyone has questions, feel free to jump in. I think you can ask using chat. So let me just make sure I can see that if you do. So if you need to ask questions, like you definitely should. And yeah, so with that, I'll launch in. So this background image here is actually of my driving simulator, which I haven't been in for a few months now. But I'm going to talk about some of the research that we do to study how people are going to interact with future automation, particularly using simulation, and some of the future work that we're doing in this area right now. I think this is particularly important for something like autonomous cars, where we're actually just defining all sorts of things about how the car should work for the people who are inside the car, but also for people outside the car. I think the assumption really early on was that the really hard problem would be teaching the cars to drive, in an environment they weren't familiar with. But now, definitely the big obstacle is thinking about how the car operates in a situation where there's not just autonomous cars, but other drivers and vulnerable road users as well. And so studying possible things that might happen is the way that we can actually get to the point that we can design better and safer autonomous cars. So this is what it's like inside my driving simulator. We have a car, a 3-screen display. My video didn't play. I hope yours did. My background actually is in human-robot interaction, and in HRI, I'm actually famous for having developed a lot of field research techniques to understand how people who haven't been trained, who haven't been involved in the purchase or deployment of a robot, how they actually respond when they encounter a robot in public settings. So here's an example of that kind of work I was doing.
Right behind you. Don't come any closer. Oh, you did. Hi. Don't come any closer. No closer. Okay. We don't have any guards. Wiggle.
okay? Are you okay? This is over here. Here you go.
So just to talk about that, what we were just looking at right there, we were using what's known as a Wizard of Oz study. So that is to say the robot, the trash barrel robot, looks autonomous, but we're actually remotely controlling what the robot can do. It's not actually hard to build a robot that traverses space autonomously and even doesn't run into people, but it's actually very difficult to get the robot to have appropriate timing when it's interacting with other people. This technique of Wizard of Oz studies was actually pioneered in Alphonse Trapanis' lab. And they actually did a lot of research in looking at natural language interaction, and they used Wizard of Oz techniques for developing speech and language data corpuses to understand like what people are going to say, so that you can actually train AI and machine learning models on the things that people are going to say. So anything that's interaction has this contingency, like what the machine is going to do depends on what the person does, depends on what the machine does. And so it's actually very difficult to design things where you have multiple stages of contingent behavior without using Wizard of Oz studies, because usually what happens otherwise is that when you have a stage in the interaction that is not well designed enough, like the interaction just breaks down. You don't learn what else could have happened or would have happened. So in the studies that we're running, you can see there's a lot of things that you just wouldn't know to anticipate. For example, that child that was trying to bait the garbage can by like using garbage and like get it to go across the room where he wanted the garbage can to be. Clearly, even though it looks like a garbage can, it doesn't look anything like an animal. The child's mental model is that the garbage can eats garbage. And in fact, it's not just like eating the garbage, but is like motivated, you know, by a hunger that you can actually use to make him do what you want it to do. And that's like a really funny thing that a child thinks that, but then actually, if you go back and think about a lot of the other interactions the adults were having, they clearly are operating on the same model. Like this idea that you can wave a chopstick wrapper like it's a dog treat and like make the, you know, garbage can come, or you're like waving garbage at the trash barrel. I mean, like that's clearly a sign that people use that as an operational model, even though they completely know that's not the literal thing that's going on. So anyone who's designing a robot trash can needs to know that that's the operating model that people use. And maybe you don't feel like going with it, maybe you have to fight that, but just to know that people have that is an important thing to know. We bring those kinds of techniques and those approaches to simulating interaction to the study of driverless vehicles, autonomous cars. And so here is a similar but different field study looking at how people who are pedestrians are going to interact with driverless vehicles. So it's a little funny. This is actually a study that was really well cited and really well known for. And it's because I think a lot of people realize the question of how autonomous cars are going to interact with pedestrians is a really important question. It's possibly more important than the question of how drivers inside the car are going to interact, because at least the people who are in the car maybe have been trained, at least have been warned or opted into like participating, in having an autonomous car. But all the other people on the road are just basically, like at the mercy of the people who are testing autonomous cars. So the question of what happens when the cars interact with them is really, really crucial. And so I think a lot of people were interested in it and like talked about it, had done virtual reality driving experiments with it. But because we were able to think about how you simulate the interaction in the real world amidst the real world context, we were able to actually like run studies where you can see that people are like looking at the car, but like it's really important to know that most people, even if they're not sure what's going on, are like walking by anyway. One of the really interesting things that came out of this study was this discovery that we don't do the thing that we say we're going to do. What everyone knows that they do is that they stand up the crosswalk and they make eye contact with the driver before they cross the crosswalk. Well, in our situation, it was actually impossible to make eye contact, and a lot of people crossed the road anyway. And when we stopped them to interview them afterwards, they didn't notice anything weird about the car. If it says something about the inattention that people usually have when they're walking down the road, a good number of people actually had to look back to see that there was a car, even though they looked at the car. We have videos showing looking at the car, but they didn't remember a car, they didn't note the car. And the really important thing to know is that they're not making eye contact with the driver, even though that's what we all know that we do. Where they're actually looking when they're trying to decide whether they should cross the road is at the front of the car. They're looking at the front bumper and the front wheel. And so if the car does something strange, you can see some of the clips are from a later stage in our experiment where we actually eased into the crosswalk after people started walking. If there's some sort of breakdown of expectation, that is actually when people look up and try to communicate with the driver. And in our experiment, a lot of times that's when they see that there isn't a driver. And usually what happens is they decide to go anyway. You can actually see the moment of indecision and then decision making and then going. And so there are studies that actually talk about the speed that people walk when they're thinking, when they're cognitively loaded or not. And we can actually really see that in our videos. But so this is a really important thing to know, that people aren't looking. If you look and put signs or robot heads or something in the driver's seat to help people understand that it's an autonomous car, it's not something that people are going to notice. And so it's like a really important thing to know, that what people are really attending to is the motion of the car. So one of the things I just really want to point out is how simulations help us to anticipate how people are going to behave in different design futures. So as engineers, we're very often trying to make things, and we make assumptions about how people are going to behave. And it's very important to check those assumptions. And ideally, it's important to check those assumptions before you've done too much building. Because if you built this whole system based on some assumptions about how people are going to act and they just don't do it, like they literally aren't looking at the place that you plan to put a display, it doesn't matter what color or font you use for that display, it's not useful. So here's an example of footage from a driving simulator run. And in this study, we're basically telling people to supervise an automated vehicle. And we saw lots of instances of this. It's not just this one woman where this happened. So the car is driving autonomously on a largely straight road. There's not other traffic. And she's not supposed to be falling asleep, but a lot of people fell asleep. The first time it happened, we thought like that is unusual. We'll just like make a note of it. We probably won't use that participant's data. But as we went on, we found that this was actually pretty common. Here's the interesting thing. In the study that this was run in, we actually had people doing 3 different activities. One, they were just told to supervise automation. That is what in almost every single place in the US and worldwide where we have automated driving, that, we basically say like you have to have a human safety driver. That person needs to supervise the car and do nothing else. In the 2 other conditions, which again is the same participants, we had them watching a video or reading passages on an iPad. And we were actually looking, the goal of the original study was to look where we should put displays to see when people transition behavior. And then it just turned into this thing where we were watching the sleepy behavior. What you can see is we had it was a within subject study. So we had same people do things and we counterbalanced the order. You can see when people are supervising the automation, and almost only when they're supervising automation, they are showing sleepy behavior. This means that they closed their eyes and actually went to sleep. We had that happen, or closed their eyes for longer than 3 seconds, which is a really long distance on the road, if you don't know. But the really interesting thing is this. Actually, there's a lot of research that shows that supervising automation causes people to become fatigued and sleepy. Like, this is something that's well known from flight simulation. The really interesting thing is this other thing, which is that when people are reading or watching video, they're not asleep. And it means that they're able to respond more quickly when they're actually asked to intervene than if you tell people just to focus on supervising the automation. So this has like really interesting things that we really, when we are having people interact and supervise automated driving, it's actually really important to give people some tasks to do rather than just tell them to watch something where mostly nothing is happening, because that makes them pass out. And so we have this, this title here, Distraction Becomes Engagement in Automated Driving. Literally the things that we are trying so hard in current day driving to not get people to do, because it's like very dangerous and it causes accidents. When we have automated driving, we have to think about how we can actually use those kinds of activities, the ones that we think of as distraction activities, as engagement activities. And that's like a really important thing to know, that when you move to automation, the interaction with the driver is a complete paradigm shift. Here's another kind of study we run. This is a study where if you're in a driving simulator and you are supervising the car, we basically come upon a, like unmarked turn in the road where there's like, not good lane markings, there might be construction or other oncoming traffic. And in those sorts of situations, in most autonomous vehicles would consider this to be the end of the operational design domain. Even if we were in level 3 or level 4 automation, that would be the case. And then we basically just see if there's some sort of emergency situation and the car asks the driver to take over, how fast and how well can they take over? And so one of the things that we're varying in our different conditions is like whether they're actually given the alert 2, 5, or 8 seconds before that turn. Another thing we often vary is the way that transition occurs, what kind of alert we use, what kind of control modality people are given. So here's an example from a pilot study. So this is a graduate student who knows that this is what he is piloting.
Emergency.
So that actually would have counted as a successful transition. So one of the things I also think is very important is not just that we look at the transitions, but the quality of those transitions. That is an incredibly stressful situation for the participant. And so like, that's one of those things that I think when we're looking at video and studying the interaction, and we should also be mindful of. When we actually look at the quantitative analysis of this kind of driving, you can see that actually when we tell people to like supervise the car, like that when they're given like very little time to transition, like 2 seconds, you can see that there's just like a lot of like steering reversals, and like they have a high road offset. But like with 5 or 8 seconds of like advanced warning, people actually do really well. And interestingly, I think in the 8-second condition, we're really at this point where the quality of the driving simulator screens becomes an issue, because a lot of times people get a warning and they look up, and if they don't see anything to be concerned about, they actually often will go back to whatever they were doing before. And so they don't perform any better than someone who is actually alerted at the 5-second level. When we actually give them some sort of passive secondary task, so this is like if you're like watching a video, people do much worse. You can see like there's just like a lot more variation in the 2-second condition, but then people are doing okay in the 5 to 8 second condition. And then when they're doing an active secondary task, like playing a video game or something where they're like mentally focused and not just like passively watching, that you can actually see now, like in that 5-second condition, people are actually starting to perform poorly. So an unstructured transition is something that should never actually happen on the road. So we're not actually trying to recreate a thing that we think will happen and understand what, have predicted value. What we're actually trying to do with this is figure out how far down the road does the car need to build to model what's happening. Because every single second you can shave off of the distance, the time that the car needs to be able to predict, like you actually are increasing the likelihood and ease of actually creating automation by orders of magnitude. It's a lot more data, there's a lot more uncertainty about what's happening like 5 to 8 seconds down the road. And so the kind of computation and power that you need to support that computation is really hard to fit into a car. It's like super hard to do in something that's not connected to the cloud. Whereas something that is like 2 seconds, like you can actually easily install. And so really something like this basically tells you something like about when we can actually have automation that people can successfully transition from well. So one of the things I really like are running naturalistic experiments. Every lab study is contrived in some way. It's not different from what we say about models. Every model is untrue, but some models are useful. So different experiments can help us understand how people are going to behave and respond and feel. And in a naturalistic experiment, you can actually like manipulate things or just like learn from things that would be very difficult in a laboratory experiment. So here's an example of the kind of things that we're doing now. We have a setup that is actually created by Nick Marlau, who's now a professor at Carnegie Mellon. When he was my PhD student, we worked on this method to prototype real-time remote interaction prototyping so that you can actually think about how you would interact with people who are in a car without being in the car with them. And so we actually are just like using wireless technology, video conferencing, not unlike what we have here, but with a different interface so that we can actually pretend to be a smart car. So here's an example of that. Oh no, here's some photos of what we have. I think we're showing this off because we can like fit everything inside of a Pelican case that we can put in the trunk of the car. So we can actually really easily instrument other people's car with this ability, and that lets us prototype people's own cars. We can actually test out how interaction would be while they're on their normal commute, and like see what we would learn from like looking at like having spoken word interactions or having different kinds of visual interfaces on people's drives. So the person who's remotely interacting with the driver is actually sitting in an office. They're given this display like what's shown over here. It's web-based, and anyone with a web browser can actually pull it up. And on that display, they have like telematics information from the car, from the OBD2 port. And we also have pre-prepared some questions that can actually be played, but also the remote person can actually just type messages and then they actually like get converted using text-to-speech and spoken to the person who's in the car. And then additional things that are here is that a person can also like remotely watch the person as they drive down the road. We have a camera that's pointed at the driver, but also a camera that's pointed out the front windshield so that we can actually like see what's coming down the road and time our speech appropriately or ask about things that are in the environment. So now maybe this is a video of how this works. So ICC is intelligent cruise control. So the brakes went on, but that was cruise control that actually was braking. Now the remote wizard is asked.
Did you feel the system intervene to brake?
Yes.
Did you feel that was safe?
Yes, I felt it was pretty smooth and it started applying the brakes about when I would have, so it was it felt early enough that I didn't need to intervene myself.
Here's another video from a run that we did in a Tesla. So, I don't own a Tesla, but somebody was test driving a Tesla. And we were just talking to him about his use of the kind of like autopilot features.
How is the build quality?
Not that good. Not that good. For I mean, this car is roughly 130 km, I think. So I think it's not good enough.
So this is something that you just wouldn't think about, right? Like the idea that like once you have autopilot, people are a little bored and they're gonna suddenly the build quality inside the cabin becomes much more important. However many like contact points that you actually felt like you needed to the chassis for the panels, like you actually need more because the person who's using an automated car suddenly has a lot more time to think about all these different things that are inside the cabin, and that affects their estimation of the overall car. A lot of times, if this person actually runs a research lab, but a lot of times like consumers don't differentiate between the different subsystems in the product and how they're performing. They just have one high level just felt feeling about how the car does. So this last bit is showing this like other novel driving simulator that we have. We really wanted to know what people are going to be looking at and thinking about when we have an autonomous car. And even though in the research garage at Stanford where we ran this experiment, there were autonomous cars, like they barely worked well enough. They were often restricted to the track. And so we couldn't actually just see how people would like look around in their everyday driving. So this is our fake driving simulator. His name is Nikhil. You can see that he's sitting in this driver's seat. We have it, we label him the driving wizard. And we just put up some foam core, black foam core here between the participant driver who's sitting in the passenger seat. And so the person who is in the experiment, we asked them to imagine they're in an autonomous car. And we have taped on the steering wheel to help like make that kind of theatrical idea clearer. And in the back seat, there's an interaction wizard who's actually running the experiment. So that person is watching the drive. There's some electronics here. We were experimenting with some vibration arrays to pre-cue people about different things that the car was about to do. But we wanted to just like see how people would feel. And that actually worked so much better than even we thought it would. So here's a video of that.
How did the dive go?
Oh, it's pretty amazing.
Go, Otto.
Oh. I guess the computer is pretty cautious, which is pretty awesome. There's a number of obstacles that I could have imagined being pretty troublesome for a computer car. It seemed to navigate through them all. A flock of people on the side of the road on this really small street, like construction and like traffic and all these different situations where it just basically did the right thing. Yeah, it was a much better driver than most humans.
So how did the ride go in general terms?
I was impressed. It went very well.
Did you feel nervous at any point?
I did. There was a construction site that we went past. There was a construction vehicle and the guy was waving for me to move. I sat there like a retard, like staring at the thing. I didn't like wave to the guy or anything. I just sat there. So I was like, I really hope the car does smart. So the car backed up and then the guy made more hand signals.
Did you trust the vehicle?
I don't know. I just don't fully trust a car to drive on its own. Even though I had no bad experiences with this car, it just seems strange to me still that a car can drive itself.
We will now turn on the autonomous control, and the car will now greet you. Car, please say hello. Did you notice the car say hello?
I did.
What was it like?
It was an engine roar.
Okay. Did it make you feel uncomfortable or hurt you?
No, I thought it was very friendly.
Was it what you had imagined?
It was what I imagined. It was smooth, cautious, but normal driving experience. Kind of what makes it cool. I think I was surprised how much I trusted it. Even from the beginning when it said hello, that one thing like gave it enough personality for me to trust it. It made me feel like even though it wasn't a human, it wasn't of malicious intent.
It just was driving carefully, slowly. Actually, it reminded me of like a driving school instructor.
Was this pattern of driving okay with you?
Oh, it was ideal. I could definitely own one of these. How do I buy one? What do you think in 10 years?
So I will say I obviously work with a lot of people that work on automotive user interfaces and intelligent vehicles. And one of the big things that people are really concerned about is trust and automation. Like, what will make people actually like trust autonomous car well enough to get inside of it? And then a lot more recently, people have been talking about appropriate trust. So making sure they're only as trustworthy, like they're only trusting the vehicle in line with what it's actually good at, and not knowing when to intervene if the vehicle actually might make a mistake. But one of the really interesting things I think that we can see in this simulation, which is not what we sought out to find, is that simple little things that we were doing as a manipulation check, like just to make sure that people can tell that whatever we're doing for our signaling is being noted, like a greeting. Like, people are not just interpreting that as like, oh, I can actually like feel this like medium in this communication. They're actually like, oh, the car said hello and it's friendly, and they actually attribute like other things to that. They're like, oh, it's not trying to hurt me because it said hello. And like, that is a huge thing, that like people might be making user-friendly interfaces, sometimes not even in the main drive system, maybe in the center console. And people have this like psychological feeling about what that means if the car says hello that we might not intend, and that will affect like the feelings of trust, like sometimes not appropriately. From the in-car experiments that we've done, like it feels a lot more like inappropriate trust, where people like literally overtrust the vehicle because it seems to perform really well 90% of the time. It's just like a lot bigger problem than the question of how you get people in the vehicle in the first place. So one of the really interesting things about the way that we approach this research is that you can just think about how the whole world is a stage where we're actually trying to stage the simulations to understand how people are going to interact with cars in the future. I think all of us researchers spend a lot of time looking at things that happen in the world and thinking about what that means for the design, and then thinking about how we can actually like learn empirically what a lot of other people would do in this situation. And so we as researchers, in order to study those things, would have to think about how to build the sets, direct the interactions, and collect the data about what is going to happen by running these, like, in the real world theater simulations. One of the things is that a lot of people are trying to study, like a lot of people are trying to talk to people in the car because they have some availability, and that's definitely going to be more the case when we have autonomous cars. And right now, and I think even when we have like situations where people are supervising automation, most of the time it's really welcome. Like, people are bored, they like to have interaction, and occasionally it's like a life or death situation where you like distract someone at exactly the wrong moment. So one of the things we're interested in is like how we can actually simulate things so we can actually build a model of when are good times to talk to people and when are bad times. So this is a study we ran where we actually like made a set course, and then every 30 seconds to a minute and a half, we actually just asked, is now a good time? And people either said yes or no. And when we're collecting a lot of data, camera data, physiological data, data from the car, GPS data, and we're trying to see like what factors actually best predict like good and bad times. So here are some of the things that we're collecting. We have the labeled response, we have the physiological signals, we have the automotive data. So from a machine learning perspective, this is a supervised learning situation. And I think we're at this point where there's a lot of really cool machine learning algorithms that could be applied. We often don't have the data that we need to like make those things useful. And so we actually have to think about how we generate the data. So here's just to show off like a super clip of all these moments that people mentioned is not a good time. It's too small to see. I don't expect you to be able to see this, but one thing is that a lot of the things that people are mentioning when they're saying it's not a good time, they'll say something like, I'm trying to make a turn right now, I'm still on the freeway. And so but there's a lot of ings, like gerunds. And it's because when people are in the process of executing maneuver, like they really just like they can't deal with this additional spoken word interaction. Whereas a lot of times, even though it's geographically proximal, like right before and after those things, like people are completely fine and happy to be spoken to. I've shown you a lot of clips of things where we just like were surprised and stuff that we never even knew to look for. And here's a great one here.
Is now a good time?
No, I'm still listening to the same song.
So the first time we asked is now a good time, the woman was moving and on the roadway, on a highway, and it was going pretty fast. And it wasn't a good time because she was listening to a song that she liked. She didn't want to talk and interrupt the song. The second time we asked, we're now actually on a suburban neighborhood road. We're at a stop sign, and it's a completely different context from almost every other way that you think about it. But the woman is actually a little bit annoyed to be asked again because she is being interrupted twice in the same song. So, I mean, that's like a thing that when people think about where they are and what the context is, a lot of times there are things that as engineers we wouldn't be thinking of, but actually for the user are relevant. So, you know, I'm going to close up by showing some stuff that we're really pushing on right now. I think if we think really creatively about how we do simulation, we can actually study things that like are very difficult otherwise to study. One great example is like we want to be able to do some of the simulation things that we're doing in the lab on the road. And one of the reasons why we want to do that, especially things like takeover studies, is that driving simulators that happen in a lab with screens basically get their immersion and, you know, like fidelity from people looking at the screens and those things looking realistic. When people are in autonomous driving studies, they're very often doing something other than supervising the car and looking at those screens. And so the level of fidelity for the simulation actually goes down for the same, you know, simulated lab because the context is such that people aren't looking at the thing that fakes the scenario. And unless you have a motion base, and even if you have a motion base, people often like don't feel like they're actually moving in a car. They can actually lose track of where they are. So this is a thing that we've built, which allows us to do virtual reality on-road driving simulation, and then you have like kind of the physics of the actual driving for free mirrored with actual virtual events.
Does this feel like kind of okay?
Yeah. Like, does it feel like I'm in a car?
Yeah.
Yeah.
All right. Can you put your hands out forward? Right.
Ooh.
And just leave them kind of center in your vision. And now you can just like, if you drive straight, you should be going just.
Oh, this is fucking weird. I should probably not drop the F-bomb.
So this other oncoming car is actually programmed to hit this car.
Oh god.
It just. It was funny. Like there was a car hitting them in VR.
Oh really?
Yeah.
Oh god. Now we drove off the world.
Yeah.
The reason why that guy had to explain, the person who was the interaction wizard had to explain that they were that there was a car is because the person who's driving is just like driving straight in a parking lot, and you know, the idea there's other things going on for the passenger is kind of interesting and surprising. So right now we're actually working on the augmented reality version of this. So we're actually able to have a person who can see everything on the road, almost zero latency, and then actually see how they drive if there are things that are happening. So we can actually use that on a track. Here's another thing that we're doing. We're actually doing an experiment where we're running the entire driving simulation in virtual reality, but we can actually put two people in that same virtual world at the same time, and then we can study how drivers are interacting with one another on the road. And we actually know just from our everyday driving that when you come to four-way stops or in all sorts of, you know, like situations where there's like something unusual going on, you're actually looking to see how the other drivers move the car to get a feeling for what they're going to do and use that to plan what you're going to do. And those things are not the same, different places that you go in the world. I mean, it's not the same between where I am in San Francisco. It's not the same when you go to a different country. And sometimes we only know that we're doing something unusual, but we don't actually know how it's different. But when we have autonomous cars and we're programming how they behave, we actually have to have cars that can actually anticipate and respond to the differences that are in different places. So one of the things we're trying to do is to study how people communicate with one another and how those things are the same in different places. So I'm going to show this next video. This is actually in Haifa at the Technion. David Good, he is the person who's a researcher, a PhD student, who's running the experiment. This is Carmel Zoltov, who's a Technion PhD, who's collaborating with us. What we're seeing on the screen behind David is what the woman on the right in the virtual reality driving simulation sees inside her goggles. And basically these two women are going to come up on a virtual four-way stop and communicate with one another. She can actually see the other woman gesture to her, so she just does that. And basically, after they go through the intersection, they're asked to rate how well the other driver, how well they drove, and how the other driver drove through that last interaction. All right, so that's what I have to show you. I haven't been able to see how you guys are reacting to it, so I'll really be excited about the Q&A part of this and kind of talk to you about my research.
Thank you, Wendy. If you have questions, you could unmute yourself.
I was wondering, how are you detecting the distance and everything with I saw you were using an accelerometer, or do you use a gyroscope, or what are you using to like detect where to stop and how?
Yeah, we do have an accelerometer. We have a lot of sensors, IMUs, like a high precision GPS unit, gyroscope. We actually need everything just like to fix where the actual car is on the road. It's surprisingly hard.
So thanks, Wendy. I'm surprised to see and notice maybe how much gesturing and voice is part of the interaction. Are those how are those as social cues part of driving or part of a future research agenda?
I think we're really interested in how people, so I did my PhD studying how people implicitly communicate with one another and with machines. And I think one of the things is that people do expect machines to pick up on implicit bodily, sometimes speech cues. And they do that even if there's no apparent like sensor on the machine that they can spy that says, that they should be able to see. So there's just a lot of there's a pretty high expectation, I think, because people just aren't thinking about the fact that they use these cues, and they aren't really thinking about how they know different things about what one another is doing. So a lot of times, for example, people use deictic reference. They point at things when they're talking to a robot. And even if you expected the robot to understand speech, when you point at something, it means that you expect the robot to see the pointer, make the reference to the object, have some understanding what that object is for and does, and then can then match the things that you said in the speech to, what you're saying about the object. And that happens all the time. People point and talk to people, robots about things that have functions or purposes and stuff like that all the time. And so that's one of the things that we basically have to think about, that people are super happy to simplify their vocabulary. They have an easier time thinking the robot has limited vocabulary than understanding that a robot or an autonomous car doesn't understand bodily language. And if you think about that, it's because that's so primary. Animals that can't speak use, implicit cues and communication. They point with their bodies. They stand near things when they need to open the door for them and stuff like that. And so it feels weird to us, as creatures, to have a machine that seems very advanced not be able to do those things.
Well, I'll take this opportunity to ask another question then.
Yeah.
So,
sure.
so I've always been interested in such novel designs and research methods that you have, particularly here, like Wizard of Oz stuff. So you have a person sitting in a passenger seat with someone to the left of them and someone behind them. Is it something that they totally see and then work past or ignore after a couple of minutes, or how do people interact with that kind of Wizard of Oz setup in the car?
Yeah, I mean, I think it's always surprising to people who don't do this kind of research to see how quickly people like basically, respond, very naturally, in these environments. And I think it's because if you think about theater or TV, like once the drama is unfolding, you basically get caught up in the narrative, and you can put yourself in the world, even if completely fantastical things are going on. And so you can see when we're interviewing people after, for example, the RADS experiment about what's happening, they have filled out a consent form that explains there's always a human driving the car. Sometimes you've even seen the person that's driving, but you can hear from the word choices that they make and the way they talk about the interaction. We set them up to think about it as an autonomous car. They're thinking about it as an autonomous car. And these are people who are, in advanced degree programs at Stanford. So these are not idiots. This is just like the natural thing to do. And so I think a lot of times people assume that the way that people are behaving might be the novelty effect. Like maybe they're just doing this because of study and it's like this weird situation. When you look at the video, you can see how naturally people seem to be behaving. And I think it's because people know how to act as if, even if it's not real.
Cool, thanks. So time for another question or two.
I want to know if there's like let's assume there's like a mechanical failure, like arm brakes on the front wheels or the back wheels of the car, and then that creates a lot of vibration or whatever. How does the autonomous know how to stop comparison to like vibrations that happen from the gravel roads and other roads?
Yeah, I think it is definitely the case that the car is an instrument in a way where it can actually anticipate every single, particularly like internal mechanical failure. So that is like right now, like literally one of the reasons why you need to have a safety driver. Even without doing that, I mean, of course, most of the cars that are on the road are in very good condition and they're like legally required to be inspected. Most of the things are test vehicles. But the first thing, like, and then default behavior for most of these, vehicles is they know how to stop. Like if anything else goes wrong, they just stop the car and they count on the traffic rules that we have where you're supposed to be able to stop in any situation, no matter what, and everyone else's responsibility is to move around you. And so there is a stop, and then there is like a default pull over to the side of the road program that every one of these things has that like is the thing that they try to do if everything else goes wrong.
If I can ask a question, there's been a number of predictions on when we're going to get to more autonomous vehicles and full autonomous vehicles in America. What's your idea on the timeline for when this technology is going to be robust enough to really be implemented even further than it is already?
It's funny, like in 2017, people were like, oh, these people who are like CEOs of car companies are saying they'll have full automation by 2020. And I was like, I would bet children I have on the fact that it won't be, and that now we're in 2020 and there aren't, and it's not because of the pandemic. I mean, I think that if you are willing to invest a lot of money in each vehicle, you could actually make a car that is safe to travel on the roadways without a human supervisor in the next 8 years. And I'm basing that based on like your ability to model the world around you and like do the computation in the car. But I don't think that it's going to be financially viable to put like, $3 million, $5 million cars on the road And so it depends a lot on like what it is that's the operating model for where the computation happens. I think if it's going to be allowed that you can have things that are based in the cloud or have remote drivers, you might see stuff in that window, but I would be really surprised if we actually have anything inside of a decade.
Thank you.
Mm-hmm. And I would say the main problem being other people. So in places where you don't have cars, a lot of stuff, and you can have really expensive vehicles, like in construction, that, you know, on farms, like you already see like full automation.
Yeah, 2 years ago in Tempe, an Uber autonomous car killed a person, and just last week, the driver, the supervisor, was charged with negligent homicide. Do you think that will set a precedent for the law, or change people's confidence in self-driving cars?
I mean, I have opinions about the way that Uber was running their test program. Like the people seem to be not well trained, you know, you know, they were the first to try to do single safety drivers, whereas, you know, like Waymo, who I feel is far ahead, you know, in terms of their ability of doing computer vision modeling, stuff like that, until fairly recently was still doing everything with 2 safety drivers. And if you look at the number of you know, events where there were accidents or little infractions, Uber had, going into that accident, a much worse record than any other car companies testing per deployment. They had a lot more intervention. So like, I don't think it's the deterrence effect that's going to make the car safer and make people feel comfortable. I think if people are worried, they should be worried. And the reason why I think they should be worried is right now, the way things are set up, the governments and municipalities are letting the car companies decide what is safe enough, and the car company can decide, you know, what the accident rate can be based on the strength of their brand and their financial situation. That shouldn't be how these decisions are made. One thing I've been a big advocate for is data sharing. I think if a car company is doing field experiments on the road, which is what I think they need to do to gather the data they need to actually make themselves safer, they should be obliged to share that data widely, because, you know, there's a cost to all of us when you know, our streets are being used as a test track, and we should get some of the benefit, and that would also allow better oversight. And that's not the case right now. Right now, very little is required to be reported, and after a really long delay.
Yeah, thank you.
Mm-hmm.
So we're about out of time, so this might be a good stopping point. Let's thank Dr. Wendy Ju from Cornell Tech for joining us. We'll pick up again next week, Thursday, 2 p.m. Thank you all.
Thank you.